Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about two examples of posterior predictive distributions for data with a Poisson likelihood. We're going to talk about the case where a gamma prior is used for mu, where mu represents the mean of a Poisson process. Okay, let's begin. First, I would like to summarize what we have done thus far. Okay? So, as we already know, to analyze data using a Bayesian approach, we need a likelihood function for the data and a prior distribution for the parameter or parameters of interest. So, in this case, the likelihood for a single observation we know that it looks something like this, right? We could think about it as a conditional probability, the probability of observing a particular value yi, given that we have knowledge about the parameter mu, okay? Given a particular value of mu. Okay, so and it looks something like this, right? We have mu to the power yi in this case, that particular value of our observation divided by yi factorial, and then we have e to the negative mu. Okay, so we know that this expression will be valid for yi equal to 0, 1, 2, 3, so on. Okay, so that's what the Poisson probability mass function looks like. Okay, so something else. What we're going to have here is, let me use the proportionality symbol here. So we're going to ignore the constants, right? Well, the constants with respect to mu, right? And then we're only going to have the terms, we're going to retain the terms that have to do with our parameter of interest. Okay. So now, if instead of a single observation we have a sample, let's find the expression of the likelihood for the case of a sample, right? We have a sample of size n, right? y1, y2, y3 up to yn. Right? What we're going to have is the product of terms like this one. We're going to have n terms that look like this one. So we have the product of those n terms. We have the first one here, we have the last one here, y sub n, and then using the proportionality symbol we're going to absorb the terms that the part of the part of this expression that doesn't have to do with the parameter of interest. Okay, so once we do the algebra, what we have here is the sum of the yi's and then I goes from 1 to n, and then we have n times mu, right? We combine all these exponentials like this, n times mu, and that's it. Okay, so that would be the expression for the likelihood for a sample of size n. Okay, now as we said at the beginning of the video, the prior that we're going to be considering is a gamma prior, and we know that a gamma prior happens to be a conjugate prior for that parameter mu that we are interested in. And by conjugate, what we mean, right, we already know that when we use that term, a conjugate prior, what we mean is that the posterior distribution will belong to the same family as the prior. Okay, so let's just underline that in this case we're using the conjugate prior. Okay, and we know that the conjugate prior, as I already said, right, is going to be a member of the gamma family. Okay, so it looks something like this. The probability density function for a gamma with parameters v and r looks something like this: v to the power r divided by the gamma function evaluated at r times mu to the power r minus 1 times e to the negative v times mu. Okay, and that expression makes sense for positive mu's, right? And we also know that there are restrictions for v and r. V and r, both of them have to be positive. Okay, so again, let me use the proportionality symbol, and again we're going to ignore the terms that make this expression, right, legit probability density function, the constant that makes it integrate to 1. We're just going to pay attention to the terms that involve our parameter of interest, mu, right? We've done this before, and we know that it's not going to affect any of what we're going to be doing here. Okay, okay, so just let me remind you that our posterior is going to be proportional to the product between likelihood and prior, right? So prior times likelihood. Okay, so in this case, we're going to have that prior, right, times that likelihood we had here, right, the one for the sample. Let's consider that one here. So in the end, as you can see, what we're going to have is something that is proportional to this. We could combine these two terms, right? So we could have plus r minus 1, right? Let's place parentheses here to make it super clear, right? And then we could combine these, the exponentials, right? So we could have n plus v times mu. Okay, and then I don't need this guy anymore. So the point is that, yeah, this expression here is the kernel of a gamma distribution with parameters r star. The new r happens to be just the old r plus the sum of the observations. And the new v star, let's call it, happens to be the old v plus n, the sample size. Okay, so those would be the updating rules. Okay, that's what we call them. Okay, so next, what we did in another video is we derived step by step the posterior predictive distribution, right? So let me remind you what the posterior predictive distribution looks like when we have this kind of situation, when we consider a gamma prior and then we end up with a gamma posterior, right? So what we did in that video where we derived the expression was we used the definition, right? So, and the definition for that guy, right, would be the probability of observing a value for a future sample of size n star, right? So the probability of observing the value x given that we have, you know, information coming from a sample. Okay, so it could be a sample of size 1 or, you know, of or a bigger sample. Okay, bigger than 1. Okay, so say that we had information coming from a sample of size n. Okay, so anyway, if we write down the definition for the predictive distribution, is going to be just an integral in this case of the following product: the probability of observing x given a particular value of mu times the posterior distribution of mu given, you know, your sample. And again, you could have a sample of size 1 or bigger than 1, a single observation or more observations. Okay, so and then we have to integrate with respect to mu, and that's exactly what we did. Okay, note that x is going to be either 0, 1, 2, 3, so on, right? Because what we're saying is we want to we're considering a sample, a future sample of size n star, but the values that that new variable could assume are the same as, you know, the values assumed by, you know, a single observation. Okay, okay, so after a little bit of math, after a little bit of math, we ended up with the following expression. What we had was this, that our posterior predictive distribution expression for that guy looked like this, right? 1 over x factorial times the gamma function evaluated at x plus r star, right? The the parameter r for the posterior, okay? Then divided by gamma, the gamma function evaluated at r, times, and here we will have a fraction where the other parameter v star is involved. Okay. And then we have something similar. Have another fraction that involves v star, and in this case the exponent is x, right? And again, note that this expression is valid for x equals 0, 1, 2, 3, and so on. Okay? So, okay, now we're in good shape. Now that we have remembered what we did before, we are ready to talk about our examples. We're ready to talk about our first example. Okay? So, example number 1. Example 1. What I want you to do here, what we're going to be doing together here, is finding the predictive posterior distribution for a particular case, okay? When r star equals 1 and v star equals 1 as well, okay? So find the predictive distribution when r star equals 1 and v star equals 1 as well. And once you have it, what I would like you to do is to use it to compute a probability. Then use it to find the probability that x is less than or equal to 2, okay, given y. Well, yeah, let's say given your sample y1, y2, yn, and so on. y1, y2, yn, okay, given a sample of size n. Make sense? Okay, so we have a future observation, right? We know that it could be 0, 1, 2, 3, so on, right? This guy x represents a single future observation. Okay? Okay. So, what we have to do is first remember that expression we have, that general expression we derived before and that we have here, is just plug in the values r star and v star for this particular case, right? So let me copy paste our beautiful expression. So in this case we have, let's plug in. So r equals 1. Well, r star equals 1, right? And v star is also 1, right? So what we have here can be further simplified, right? Let me keep the support. So remember that since x goes from 0 up to infinity and x assumes only integer values, x plus 1 is going to be a positive integer, right? So one of the properties of the gamma function is that if you evaluate the gamma function at a positive integer, gamma of x plus 1, since x plus 1 is an integer, is going to be equal to the number minus 1 factorial. So in this case, this guy happens to be the same as x factorial. Okay, so recall that this guy here, in this particular case, the gamma function evaluated at x plus 1 is going to be the gamma function is just going to be, in this case, x factorial, right? Okay, and then for instance in this case, gamma evaluated at 1, right, is going to be the same as 0 factorial, right? And 0 factorial is just 1, right? Okay. So when we have that, right, let me simplify that expression again. You can see that the x factorial will cancel out. This is going to be just 1 because that's 0 factorial, right? This is going to be the same as a 2 to the power 1. Well, I'm sorry, 1 over 2 to the power 1. That's just 1/2, right? So we don't need that exponent there. Okay, so we can see that these guys cancel out, so we end up with that expression. Make sense? Okay, so now let's find that probability that we want. What we want is the probability that that future observation is less than or equal to 2, right? So what we have to do is use that expression and evaluate it at 0, 1, and 2. And that is going to give you, it's going to give us the probability that we're looking for, right? So that's going to be the same as this evaluate it at 0 plus you evaluate at 1 plus you evaluate at 2. Make sense? So let's find those three terms. It's going to be easy, right? So that evaluated at 0 is going to be just this, which is going to be just 1/2, right? Let's evaluate at the next value at 1. Okay, so when we have that, we have 1/2 times 1/2, that's just 1/4, right? And the next one is going to be evaluate at 2, right? So we have 1/4 times 1/2, so that's 1/8. And finally, what we need is the sum of these three terms, right? So the probability that we want is given by 1/2 plus 1/4 plus 1/8, right? Okay, let's find it. 1/2 plus 1/4 plus 1/8. Okay, so 0.875. Okay, so that's one way of doing it. Let me point something out. Maybe some of you have already seen it. When you see that expression, you go, I think I've seen this before, right? X starts at 0, and then the next term is, just you just multiply this guy by the same factor to get the next guy, right? So that seems to be a geometric series, right? And if you think about this, from a probabilistic perspective, this guy is what we call a geometric distribution, right? But remember that for instance, you could define a geometric distribution if the random variable of interest is the number of trials before your first success. And if you define it like the number of trials before your first success, then you have to try at least once. However, if you redefine that discrete random variable, but in terms of something different, instead of the number of trials until your first success, if the random variable of interest is the number of failures before your first success, then this is the expression that you end up with. Okay? So let me show you something interesting here. Let's type help and let's see what we have for that function. dg_om would give you the distribution of a geometric as the one that is used here in R. Let's see how it is defined. So we have a geometric distribution. The support of that random variable is the same as the one that we have here. It goes from 0, 1, 2, up to infinity, right? And note that the expression that they use, the probability mass function for their geometric, is p times 1 minus p to the power x. P times 1 minus p, 1/2 minus 1/2. I'm sorry, 1/2, and then we have 1 minus 1/2, that's 1/2, right? To the power x. So it turns out that that's the expression used in R for a geometric random variable. So, but again, note that the interpretation of x is the number of failures until you observe your first success. Okay? So now let's try and use R to come up with the answer for our problem, right? So now we realize that the posterior predictive distribution in this case has a geometric distribution. Okay? So if we want to find that probability, the probability that x is less than or equal to 2, we want to find the probability that a geometric random variable is less than or equal to 2. Okay, so first let's create a list with the outcomes of interest, right? So 0, 1, and 2, right? If we use the dgom function, we're going to be evaluating the probability mass function at the points that we defined, 0, 1, and 2, and we know that the parameter p, probability of success, is 1/2 in this case, right? We have it here. That's expression, right? So clearly, probability of success 1/2, 0.5 is the same as 1/2, 0.25 the same as 1/4, 1/8 the same as 0.125. So we want the sum of these guys. So that would be one way. The other way is realizing that that event, the probability that x is less than or equal to 2, is the same as evaluating the CDF, right? In this case, the CDF of a geometric. And it turns out that there's a function to evaluate the CDF. It's pgom. That would give you the evaluation of a CDF for a geometric random variable, right? So we want to evaluate it at 2, and the probability of success 1/2. There we are. So same, right? Okay. Now I would like to talk about another example, okay? But before we talk about that other example, before we discuss our second example, let me remind you what the probability mass function of negative binomial looks like. So if x represents the number of failures, again failures, until you observe your first n successes, okay, the probability mass function, and remember that we use the term probability mass function because we know that this guy is discrete, okay? So the probability mass function for that random variable is given by this. N plus x minus 1 factorial divided by x factorial times n minus 1 factorial, and then we have pi, where pi represents the probability of success for a particular trial. We want to have n successes, and then if we have n successes, we're going to have some failures along the way, and since what we said here is that we're going to observe x failures before observing our n successes, the exponent is going to be x here, right? And this expression, the support of that probability mass function is 0, 1, 2, 3 up to infinity. Okay, so that's the probability mass function for a negative binomial. Okay, so now let's talk about our second example. Example number 2. So now what I want you to do is to find the predictive posterior distribution when r star equals 3 and v star equals 3 as well. Okay, and just like before, once you have it, I would like you to use it to find a probability. Find it, then use it to calculate the same probability as before. The probability that x, future observation x, right, just 1, is less than or equal to 2. Okay, given again your sample of size n. Okay, okay. There we are. So, solution, just like before. Well, here, no, it's here, right? Here we have the expression, the general expression for the predictive posterior distribution in this kind of situation, where we have Poisson data. So first step, let's plug in the values that we have for r star and v star. Okay, so we have 3 here, we have 3 here as well, we have 3, we have 3, we have 3, and that's it. Okay, and we have a 3 here as well, right? Make sense? Okay, then just like before, we're going to simplify that expression a bit more using properties of the gamma function. So in this case, again, x is an integer. We have that integer plus 3. We're going to have here inside, we're going to be evaluating at a positive integer. So this guy, gamma evaluated at the gamma function evaluated at x plus 3 is going to be the same as n minus 1 factorial, where n would be that guy, right? So in this case, we're going to have x plus 2 factorial, right? This one here, gamma at 3, is the same as 2 factorial, right? So let's simplify that. So we have x plus 2 factorial. We have 2 factorial here. Okay. Here we're going to have 4. Here we are going to have another 4. And that's it. Right? Okay. Now, let's go back to the expression that we have for the probability mass function of a negative binomial. I think we have it here. So here we have x factorial n minus 1. Here we have m plus x minus 1. Okay? So pi to the power of n, 1 minus pi to the power x. So if you compare that, let me copy paste this to make the comparison easier. Let's paste it here. So it seems, right? Note that the sum of these guys equals 1. So we have that pi plus 1 minus pi, that's also equal to 1. So, or in other words, the complement of 3/4 is 1/4, right? Here, x, we have x, and here we have 3. So it seems that we have a negative binomial with parameters n equals 3, right? And probability of success 3/4, right? We can check. So if n equals 3, n minus 1, it's going to be 2 factorial, and then the sum of these guys, right? X plus this is going to be the right value, right? X plus n minus 1 is the same as n plus x minus 1 factorial, right? So again, we have that this predictive posterior distribution happens to have one of those popular distributions, those that we studied back in sta360 or sta257. Okay? Okay. So let me just point that out, right? That this guy, our posterior predictive distribution, has a negative binomial, or is a negative binomial random variable. It's another way of saying it. It's a negative binomial random variable. Well, x would be the one that is a negative binomial random variable. Okay, so negative binomial random variable with parameters r star, well, n, that's the one that we're using, 3, and pi is going to be equal to 3/4. Okay, are we good? Okay. So now what I'm going to be doing is, you can try and do this step by step by hand, right? Similar to what we did with the example with the geometric distribution. but what I'm going to be doing here is I'm going to be skipping that part. You can do it on your own, no problem, right? All you have to do is evaluate just like we did before 3 times at 0, 1 and 2 to find this probability of interest, right? But I'm going to skip that part of doing it step by step, kind of by hand, and I'm going to be doing that directly using R. Here, let me show you. Let's type help the n binom. This stands for, as you can imagine, negative binomial, and this is that distribution we're interested in, right? The negative binomial distribution. Okay, so we want to evaluate at the same points 0, 1 and 2. Okay, so x remains the same as before, 0, 1 and 2. Okay, and as you can imagine, right, let's take a look at this. We have to check that those guys that programmed this in R are using the same expression for the probability mass function. So we have the gamma function evaluated at x plus n divided by the gamma function evaluated at n times x factorial. That's the normalizing constant. And then we go, oh yeah, no problem. We know that using properties of a gamma function, the gamma function evaluated at x plus n is going to be the same as n plus x minus 1 factorial, because we have an integer, gamma evaluated at n minus 1 factorial times x factorial. So they are using the same thing. We have p to the power n, and then we also have the complement to the power x. Okay, and the support matches. So these guys, the guys that programmed this in R, are using the same expression, so we can use that function directly. Okay, so just like before, what we could do is just evaluate the probability mass function at x. As we saw, the probability of success in our case is 3/4. So size is n, those are the parameters, n equals 3. Probability of success 3/4, right? And then if we want the probability of x being less than or equal to 2, just add them up, 0, 1 and 2. There we are. As you can imagine, instead of doing this, we could use the Pn binom function. We want to evaluate at 2, the size, meaning n, the parameter n is 3, the probability of success 3/4, same thing. Okay, so if you have time, just evaluate those three points 0, 1, 2 using this expression that we had here, and check that you end up with the same result as using directly from R the n binom function, or the Pn binom function, negative binomial, right? Okay, so let's summarize what we did here. What we did is we started with that generic expression for the predictive posterior, for the posterior predictive distribution for data with Poisson likelihood, right? The one that we derived in another video. And here we applied that formula that we derived for 2 particular cases. And in one case we ended up with geometric distribution. It turned out that the posterior predictive distribution had a geometric distribution, and in the second example what we saw is that the posterior predictive distribution had a negative binomial distribution. So both of them are examples of probability distributions that we have seen before that are well known, that are popular. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.